Lorenzo di Pietro, speaking about boundary F-theorem for quantum field theory in Untitled Chapter.
Thanks a lot. Thanks for organizing this nice workshop and giving me the possibility to present my work. So yeah, today I will tell you about a paper that we are trying to finish with this gentleman. And so since it's still work in progress, any comment is very welcome. Okay, so this is the outline. I will actually spend, I guess, around half, or a little bit more than half of my talk in the introduction. So I want to give you some motivation for why recently I've been interested in studying quantum field theory on ADS background. And I will discuss also some motivating examples. This will give me the opportunity to also review some other recent work that we did in this business. Then in the second part I will introduce the main idea of the upcoming work, which is to study the partition function on ADS background, and I will tell you about the conjecture that we have, that this quantity is monotonic when we do RG flows on the boundary. And finally, if we get there, I will show you some application to long-range Ising and some two-dimensional models. But okay, it's not so important that I finish everything, so please stop me at any point with questions so that we make it more lively. Okay, so let's start with the first part, as I said, the longest part, in which I want to motivate why quantum field theory in anti-de Sitter space. So this is a workshop about boundaries, but I guess maybe most of you perhaps are more interested in boundary in the context of conformal theories, let's say, boundary conformal field theory. Well, here the idea is actually that we want to try to use the boundary of ADS, as a way to learn about massive quantum field theories, okay? So we want to go beyond the conformal case. In a sense, however, we still use techniques that are very familiar from boundary conformal field theory, because the conformal symmetry is still going to live at the boundary, but our bulk is going to be massive, okay? Oops. Okay, also now to go back. And this is a reference where, in a sense, all of this set of ideas kind of started. Okay, so just a few introductory words. So massive quantum field theory, I just mean that I want to consider quantum field theory with some non-trivial RG flow, and perhaps the most interesting setup for me is going to be the one in which we have full control at short distances. So we have perhaps some Lagrangian, everything is understood in the UV, and we have some weak coupling G that we can use to do perturbative expansion. But this only works, so suppose this G has some positive energy dimension, this only works as long as this dimensionless combination is very small, and then as we decrease in energy, at some point this becomes order 1, and we are lost when we need to study the theory at long distances, okay? This is of course very familiar. And then we have the problem of understanding how to compute observables in this theory at large distance, okay? So for instance, scattering data, such as the spectrum of particles and correlation functions at long distances, okay? So this is the kind of problem. Of course, it's a very familiar problem that one encounters everywhere in quantum field theory. Okay, so what I want to do is that I want to take this setup and put it on the background of Euclidean anti-de Sitter space, which is a fancy name, of course, for hyperbolic space. Here I'm just setting the notation, so my boundary is going to be x, Poincare coordinates, flat slicing. So x is Rd, and then we have the z radial coordinate, which is positive, with the boundary at z equals 0, and the L is the radius of ADS, okay? So one thing that is nice is that, okay, simply by introducing this additional scale, okay, for free, I can start talking about now this dimensionless combinations, okay? Before I had this coupling G, and now I can form this dimensionless combination, okay? And having a new dimensionless parameter is something that we cherish in theoretical physics. So we can take this dimensionless parameter and start doing, for instance, perturbative expansions when this is small. Okay, it's already nice. But you can say, okay, you didn't have to go as far as considering hyperbolic space to do this. Okay, you could have done it in any background. For instance, you could have just taken a periodic box. This would be good enough. However, compared, for instance, to putting my theory on a torus, a nice thing is that here I also have a number of space-time symmetries, which is the same as flat space, okay? Which is not what I would have if I put the theory on a torus. Okay, so this is an advantage. Then you can still complain and say, okay, but why hyperbolic space? You could have done it on a sphere. The sphere is also nicer. We are all more familiar with spheres, I guess, and with hyperbolic spaces. But compared to the sphere, there is another advantage that we have infinite volume, okay? Actually, all of these things, also Riccardo mentioned them yesterday in his Gong show, but okay, he only had 2 minutes, so now I can go a little bit slower. So here we have infinite volume, and this is nice, because if you're on the sphere, I mean, it's not so clear how to define stuff like symmetry breaking. Well, here we can, right? Because we can fix the value of, let's say, some scalar operators at the boundary and say, okay, this takes a VAB. On the sphere, it's a bit unclear what we mean by saying that something takes a VAB. And we can also define asymptotic observables, which are a bit similar to scattering amplitudes, okay? So the scattering amplitudes, what do I mean by the analog of scattering amplitudes? So something very natural we can do in our quantum field theory in anti-de Sitter is to start taking operators inserted at the conformal boundary, okay? And compute correlation functions. And then, as long as we are not doing something that breaks the isometries, these correlators are going to be covariant under the isometries, which means that they are covariant under conformal symmetry, acting on the boundary. So we can say that for any massive quantum field theory, we get this boundary CFT, okay? So some people, this nomenclature is a bit, perhaps, not perfect. Some people object to the use of the F, because they say that we shouldn't use F because there is no stress tensor, so it's not local. Some other people object to the use of T, because they say that this is not really an independent theory, right? It's only defined as a set of correlators in the bulk theory. But okay, I need to use some letters, right? So at the end, I will use all of them, and that's it. Then you can decide. So yeah, maybe a more precise nomenclature would be a set of boundary conformally covariant correlators, but okay, it's a bit long. So the data of this BCFT are fixed in terms of these bulk couplings, okay? So I need to give you the value of all the bulk couplings in the units of the radius, and then the data become calculable or fixed. However, not uniquely, because typically we have discrete choices. Sometimes they can even be continuous, but most of the times they're discrete. I have some discrete choice of boundary conditions for my theory, okay? So for any value of the coupling, we have several possibilities. Also, to avoid possible confusion, let me stress very clearly that the differences with the setup of ADS-CFT. So here we are having a quantum field theory of rigid anti-de Sitter space. We don't have dynamical gravity. So many things are similar, but some things are different. So for instance, we don't have a stress tensor at the boundary. And there is no claim of any kind of duality, okay? So we are just saying that these boundary correlation functions are a subset of the observables that we like, a subset of the observables of the quantum field theory. There is no claim that this is the full set of observables, or that there is a duality between some CFT and some observables in the gravity theory, okay? It's just like S matrices for quantum field theory in flat space, okay? That's the way to think about it.
Take advantage of something,
yes?
of the tools, or
you mean
philosophy of holography, but you take all the tools that were developed and...
Well, I would say that actually many of the things that we do when we do the SCFT secretly don't really rely on the metric, so we are doing quantum field theory in ADS when we do many calculations, but then, yeah, I mean, the language is of course very similar. Yes?
Since you're being pedagogic, logical. So before you mentioned quickly that in infinite volume you can have phase transitions.
Yes.
And you were mentioning the taking boundary condition, but it is a bit different, right? In flat space we take a Prof symmetry breaking boundary condition, and then we can send it to infinity, and if the correction length is finite, we can check whether the path stays ordered or not. And so we distinguish the phase.
Okay.
And yes, if you take a symmetry breaking boundary condition, the expectation value of your field is already different from zero. It's not different.
But I mean, in a sense, you're saying by taking the, I didn't understand. You want to change the radius of ADS, or you want to keep the radius of ADS fixed?
So, if we fix the radius of ADS,
yes,
and we take just a boundary condition which is symmetry breaking, that doesn't tell you whether there is a phase transition or not, because also in the unbroken, what we would call the unbroken phase, the boundary condition, the breaking of the boundary condition gives an expectation value. It's like finite volume physics in this sense.
But I mean, if you have you should consider the case in which you have some symmetry in the bulk, okay?
Yeah.
And then if you can have boundary conditions that preserve the symmetry or that break the symmetry.
Yeah.
And if you choose the one that preserve the symmetry, all charge operators will not have one-point functions.
Yeah.
Okay, and then I mean, it could be that in some, depending on the radius, you also have the possibility of imposing boundary conditions that break the symmetry or not. And then changing the radius, this boundary condition might be available or not available.
Yeah, so it doesn't look like, I mean, you spend very few words on it, but it doesn't look like flat space, right? It's not subtle. In flat space, boundary conditions decouple from the bulk physics state. You just use them in order to force the system in a phase, and then you ask if it's stable. Here, if you don't change the radius of ADS, it looks hard to do that.
Yeah, I mean, yeah, maybe the thing that is somewhat analogous to phase transition is that the possibilities for what you choose as boundary conditions change as you change the radius of ADS. Okay? On the sphere, I won't be able to discuss this. Okay, so the philosophy is that we really want to insist on this set of conformal correlators to try to set up some kind of CFT approach to the dynamics of massive quantum field theories, okay? So here this is the ADS, it is tiny and then it becomes big as measured by this dimensionless combination, let's say. And so what is the idea? The idea is that we first study our theory of weak coupling, okay? So we understand, since we are at weak coupling, hopefully we're able to understand what are the possible boundary conditions. We can study the associated set of boundary conformal correlators, what are their symmetries. If they have some mean-field theory limit, we can control it. We can understand what is the light spectrum, and perhaps we can compute the data perturbatively, okay? So this is all very well defined and doable. And then, okay, of course, the actual goal is at strong coupling, in which we would like to understand, out of all these possible boundary conditions, what is their fate. Usually in flat space, we don't discuss several possible boundary conditions, right? So perhaps we expect that only one of them survives in the flat space limit. And then if a boundary condition is continuous, hopefully we can try to extrapolate the data to get the data of the theory in flat space. For instance, the scaling dimensions of operators in a boundary conformal field theory in the limit of large radius should scale like the mass of particles in flat space times the radius of ADS, okay? So for instance, if we're so strong that we can plot the dimensions as a function of L, we should see that at some point they shoot up linearly, and the coefficient gives us the mass, okay? Of course, we need some tool to go to strong coupling. One possibility is to use, for instance, the numerical conformal bootstrap, and so using all of these as an input, and then using the numerical techniques to try to go to strong coupling, okay? This at the moment is more like a philosophy rather than something that has been done in many examples, okay? It's like a hope.
Are the ordinary unitary bounds valid?
Yes, the theory is unitary. There is all, you can use the usually.
Take L to be very small, delta can be arbitrarily small.
Again?
Take L to be very small.
I mean, this is only valid in the limit of large L. I mean,
okay.
in the limit of large L, the dimensions should shoot up linearly with L. Yes, yes.
But if they can be very small, it approaches the unitary bound.
Yeah. There are cases in which, for small radius, some dimensions. So it could be that some boundary conditions that exist at some point they become non-unitary, so you don't consider them anymore. Okay. Now, still in the motivating part, I want to give you some examples. So one very nice example, in my opinion, is to study gauge theories in Untitled Chapter. So this started a long time ago, already in 1990, Kallan and Wilczek proposed this. And so just to give an example how these things can work. So let's say we consider Young-Mills radius 4, okay? And so we start from the weak coupling end. So in the weak coupling end, we ask ourselves, so if ADS is very small, what are the possible boundary conditions, okay? And we already heard also from in the previous talk. So we can impose a Dirichlet boundary condition, which means that our gauge field will decay like this, like Z at the boundary, and we'll have this operator J, which is a constant current. Okay, this is what is more commonly used in the ADS-CFT literature, let's say. And then what do we get? We get that this is a current of a Young-Mills global symmetry at the boundary, okay? And it has protected dimension. However, another interesting possibility is to instead consider this other boundary condition in which the guy doesn't decay at the boundary but goes like a constant. And in this case, this coefficient here is an operator which will not gauge invariant one, but okay, which plays the role of a three-dimensional gauge field. Okay, so with this other boundary condition, which is Neumann, the Young-Mills is also gauged at the boundary. And then, what are instead the expectations in the opposite end of strong coupling? Okay, in the opposite end of strong coupling, we expect that there should be color confinement, which means that the asymptotic states should not have any charge under the color group. And this is clearly at odds with the Dirichlet boundary condition, right? Because in the Dirichlet boundary condition, we have this global symmetry under Young-Mills that organizes my asymptotic states. And in this paper, 2012, it was recognized that there is this clash, and they proposed that as a result, this boundary condition should lead to a kind of discontinuity as we increase the radius. So this means that there should be some deconfined phase when the radius is small compared to the Young-Mills scale, and then we transition to a confined phase at large radius. Okay. On the other hand, if we impose Neumann, there is no reason to expect any discontinuity, and it's reasonable to expect that in this case the boundary conformal field theory is continuous, and we can go all the way from weak coupling to strong coupling. Okay, it's a reasonable thing. So yeah, that's. Now the question is how do we make this end agree with this end? Okay, so we need to propose some scenario for how things work in the middle. And this is a very reasonable scenario. A very reasonable scenario is that what happens is that there is a Dirichlet boundary condition, the Neumann boundary condition, and Dirichlet at some point undergoes some merger and annihilation, okay? Which means that there is another boundary condition whose nature at the moment is a bit mysterious at weak coupling, okay? Perhaps at weak coupling is not a unitary boundary condition, but at some point it becomes one. And then the idea is that these two have the same symmetry, and they merge and they become complex, okay? So they stop existing. And then only Neumann. So after this happens, the only available, or like let's say the most natural boundary condition we can impose becomes Neumann, and this Neumann extrapolates to flat space, okay? So that's one natural thing to conjecture. And so in some recent work, what we did is to try to test this idea with some perturbative calculations, okay? So we are around here, but we see some hints that this is the right direction. We did it with Ricardo in the audience and some other people, both in Fiori and Mills and in QCD. And also more recently, with Marco in the audience and other people, we also studied this setup using the numerical conformal bootstrap. And it also seems to favor this kind of scenario. I don't have time to, because I chose to talk about something else, so I cannot review in detail in what sense it's favored, but you're welcome to ask me afterwards. What I want to stress, because it's going to be important for the more recent work, is that in order for this scenario to work, we also have a set of boundary RG flows that must exist for the consistency of this picture, a set of boundary RG flows that exist connecting these various boundary conditions, okay? So let me explain this a little bit. So what is this idea of merger annihilation about? The idea of merger annihilation is that actually there is some boundary coupling, okay, that when we are here in this region, before the transition, it has two zeros, okay? One of these zeros is this mysterious Dirichlet star boundary condition. This is a repulsive zero of the beta function. And then there is Dirichlet instead, the more familiar Dirichlet, which is the attractive zero of this beta function. And you see, we can flow from Dirichlet star to Dirichlet, while on the other side, we go to Neumann, okay? And then as we approach the transition, this parabola goes up, goes up, goes up, and then, tack, we just go to Neumann, okay? That's the idea. And this means that, you see, before the transition, we must be able to do these RG flows from D star to D, and from D star to Neumann. And this also means that when we are very close to the transition, the fact that D and D star are so close means that presumably we can also flow from D to Neumann, okay? So, you see, the consistency of this picture implies the existence of all these RG flows between boundary conditions, okay?
Is the Neumann boundary condition also zero of this beta function?
Yeah, well, you can imagine it. It's not so clear where it sits on this, but I'm just saying that, you see, if you look at this repulsive fixed point, you can perturb on one side, on the other side.
Yes.
It could be that from the point of view of this coupling, this sits at infinity. I mean, this depends a bit on how you precisely define the coupling. But okay, there must be some endpoint of this RG, right? And the natural endpoint of this RG is Neumann.
But beta should be zero, otherwise it's not at this point.
Yes, but this sometimes happens.
Imagine that at some point this curve goes down.
Huh?
You should imagine that maybe at infinity, but this curve should go down. And,
Yeah, but you know, you can also do redefinitions of coupling. Sometimes, you know, things.
something that is infinity is
Yeah.
equivalent to zero.
Yes, I mean, if you redefine the cup, I mean, of course, this would require to know the beta function for arbitrary large values of y, which we don't. But I'm just saying there should be a fixed point here, right, at the end of this, and the fixed point at the end of this is presumably Neumann. Yes.
If there was some notion of S duality, you might expect Dirichlet and Neumann boundary conditions to get exchanged. Is there some?
Yeah, that is a very nice thing that would be nice to know if there is some version of Montone and Olive for. So okay, of course we don't. So we know that there is S duality for Maxwell, right, for a billion gauge series in 4 dimensions. We know that in flat space there is no such a thing for EM mails. And okay, the simplest way to say it is, okay, there is no coupling, there is no massless coupling, right? There is just lambda EM mails. What do I do with it? Now, in ADS, you do recover something dimensionless, which is this thing, which you can also think as the Yang-Mills coupling normalized to 1 over the radius, right? You could ask, is there any kind of electromagnetic duality that can act on this? Of course, I don't know. It would be very nice if this is true, but I have no idea. Yeah, if this thing would exist, it should exchange Dirichlet and Neumann, I guess.
Lorenzo, can I ask you?
Yes.
Are you working on this Euclidean signature? Or?
Euclidean, everything is Euclidean, yes, yes, yes.
Everything.
Yes.
Can you push it on Lawrence?
Well, at the moment I didn't have the motivation because I didn't try to compute any Lorentzian observer, but for instance, if you really want to compute scattering amplitudes in the limit of large radius, yeah, you need to consider also some rotation to Lorentzian. Yeah. But I mean, there is no difficulty, right? I mean, we know how to rotate it, how to do weak rotation in ADS, it's not a mystery.
So, if there was such a notion of S duality,
Yes?
shouldn't you see also that the Neumann boundary condition becomes inconsistent for lambda L very small?
Okay, you could. I'm not sure. Like, I didn't think about that so much, but it would be nice to understand if there is a room for some version of it. So I cannot say more at the moment, actually. Yes.
Should one worry? I mean, you are using the language and the intuition of local QFT.
Yes, yes, yes.
But the boundary, the fixed point of the boundary is non-local.
Absolutely.
Should they worry about this? I mean, I could imagine other things maybe happening.
In
When
what
I
sense?
extrapolate between the two phases to non-local terms. Not here in the other.
You mean when I was talking about the RG or?
Well, both in a sense, but here you are assuming that there is a phase transition as in a local.
Yeah. Well, I mean, the full theory, of course, is local. They have a Lagrangian in the bulk, and then I can have boundary terms.
Right.
And I mean, the way I understand RG in this setup is that when I do a step of my RG, I can generate also operators on the boundary. In this case, step of the RG means changing the radius a little bit. But yeah, I don't know that anything particularly exotic can happen. I mean, the operators that I can generate at the boundary like in this way, but doing a step of my RG, which means increasing the radius, are going to be local operators as far as I know. Like, I cannot generate something non-local. Okay. Okay, then I want to mention one more example, which is, let's say it's a bit similar. If you want, it's usually very common as a toy model for young males, which is the sigma model into dimensions, right? We just take scalars that are valued on a sphere, okay? What is the similarity to young males? Also this theory, right? When we study aerobic coupling, we think that it has massless stuff. But then when we actually solve it, we see that it doesn't have massless stuff, it has a mass gap. And at weak coupling, no, this looks like it has Goldstone bosons and the ON symmetry is broken. But when you actually solve it in 2D, in flat space, you see that actually the symmetry is there, is not broken, and everything is gapped. Okay? So now let's put it on ADS. So there are various possible boundary conditions. In this case, instead of talking about weak coupling and strong coupling, I can just study the theory at large n, okay? And I can solve it at large n. So there is a possibility which is a Dirichlet boundary condition that breaks the ON symmetry, a bit what we were discussing with Marco before, which means that my field approaches a constant at the boundary, and then there are fluctuations which scale like z, okay? You see there is a gap here between the constant and the fluctuations. These fluctuations are Goldstone bosons, which are transverse to my BEV. And interestingly, they are marginal operators, okay? So this one thing that happens in ADS is that when you break a symmetry, you get some kind of conformal manifold, which in a precise sense is a trivial conformal manifold, meaning that there are many CFTs, you can move between them, but all of them have exactly the same spectra, okay? It is just the BCFT translation of a manifold of aqua in the bulk. Okay, and then there are instead more ordinary OM-preserving boundary conditions, in which instead there is some non-trivial delta, okay? And this happens because you dynamically generate a mass, okay? And the mass is proportional to the dynamically generated scale that you get out of G. And you have to solve this equation, and you find two solutions, one which is smaller than 1/2 and one which is bigger than 1/2. The two usual boundary conditions for a scalar in ADS. Okay, both of these exist. They both exist, but they only exist, so one thing that I should have said, that this only exists when lambda, the dynamically generated scale, is sufficiently small in units on the radius, okay? Because indeed, when we go to large radius, we know that by polynomial mean bug that there shouldn't be any symmetry breaking, there should be a mass gap. And so this clashes with the symmetry breaking boundary condition, okay? It's a bit similar to the clash that we had before between color confinement and Dirichlet boundary condition.
sorry, is there something interesting happening for n equal to 2? Because in that case, you still have no symmetry breaking, but no mass gap.
Well, this in this setup, I was working at large n, so that is maybe n equal to 2. N equal to 2. What is it? It's a free scale. Yeah. Okay, this could be studied, but I haven't done it. Yes, it should be easy to accept. So yeah, here we expect that for small, when we impose this spontaneous symmetry breaking Dirichlet, we have a transition between the gapped one preserving phase and the spontaneous symmetry breaking phase. While if we impose the Dirichlet boundary condition, it is symmetric, this is continuous, okay? That's the idea. And again, what is going to be, so that's the picture, right? We have, as a function of lambda L, we have the spontaneous symmetry breaking Dirichlet, and at some point it merges with the symmetry preserving Dirichlet. And here the spontaneous symmetry breaking Dirichlet, at each point, it's actually a whole sphere of boundary conditions, but it's like a conformal manifold, but they're all the same, okay? They all have the same spectrum, so it's a simple conformal manifold. This drawing we can actually compute at leading order at large n. It's not anymore a guess like we did for bits. Yes?
Maybe that's the point. Just at some point, the Neumann conditions go to the Dirichlet.
Right. Yes. So because if you compute so here I'm plotting as a function of lambda L, yeah. Right? And then what am I trying to say? Let's see.
They just don't exist anymore at some point.
Yes. So you need to look at the gap equation that gives you basically the solution for the mass as a function of this. And you discover that here the solution exists only if you use the propagator with Neumann boundary conditions. Okay? Then at some point they only exist if you use the propagator with Dirichlet boundary condition. Okay. And again, you see, we have a non-trivial statement of RG flows existing between them, okay? Which are necessary to make this picture consistent. In this case, what happens is that I'm able to flow from the symmetry preserving boundary condition to the symmetry breaking one, as long as the symmetry breaking one exists, with a symmetry breaking relevant operator. Okay? So I can turn on this deformation, and I have this non-trivial boundary RG flow. Okay? So now I'm done with the examples and with the introductory part. So it's a good time to, if you have questions. So this is just the operator in the vector representation of ON. Okay, so now I want to discuss this idea of considering the DS partition function and the conjecture that this is monotonic. Okay, so in the examples that we saw before, I tried to tell you that a crucial ingredient to check or to understand the extrapolation to strong coupling in large radius is the existence of these boundary RG flows between various boundary conditions for a fixed bulk theory, okay? And this motivates us to understand better when flows between different boundary conditions are possible, okay? So in general, okay, this may be too pedagogical for this audience, but okay, in order to have constraints on possible RG flows, one thing that is very convenient is if we know that there are monotonic quantities, like the famous C in 2 dimensions and A in 4 dimensions, and of course there are also similar quantities in odd dimensions. And the idea is that, okay, we want to find a function that goes from the set of fixed points to some number, and that it decreases, okay? If we know that, we can rule out the existence of some RGs, okay? And the interpretation is, the physical interpretation is that we can view this as a rigorous way to count degrees of freedom. And, okay, this is a bit technical, but just because it actually motivated us in the first place, this quantity also has a special role in the case of supersymmetric theories. Often in supersymmetric theories, when one studies an RG flow, one encounters the problem of determining the superconformal R symmetry, a special R symmetry that belongs to the superconformal algebra, and it turns out that this problem is solved by extremization of some quantity. Okay, and this quantity that is extremized, it always turns out that it's also monotonic along RGs. Okay, so it's famous for the case of A, for instance, what is covered in this paper. Okay, so in this upcoming work, what we do is that we propose a quantity, which is now a function from what? From the set of all possible boundary conformal field theories. And this set is defined for a fixed given bulk theory. All the couplings in the bulk are fixed, okay? So I'm not gonna start changing the couplings in the bulk, the radius. Everything is fixed. We just have a set of possible boundary conditions. And to each of them, we want to assign a number that organizes them, okay? And the idea is that this quantity is going to be monotonic along boundary RG flows, okay? So again, the radius is fixed, we just plot the boundary. We stumbled upon this idea because we were studying, earlier this year we were studying the supersymmetric case, and we encountered a quantity that we needed to extremize in order to find some R symmetry in the superconformal algebra. And then, I mean, since this never fails to also be a monotonic quantity, we said, okay, this must be a monotonic quantity. Another motivation is that, I didn't have time to review this, but there is a very large subclass of quantum field theory in ADS, which is known as BCFT, meaning that if you put a conformal field theory, yes?
Is this supposed to also apply to the flows between like D star and D that you were describing? Like
yes, absolutely.
So it doesn't assume unitarity.
Again?
It doesn't assume unitarity. This
no. What I meant is that I didn't mean that this star is always non-unitary. Okay, so what I said before is that it could be, since it's a bit mysterious the nature of this star with coupling, it could be that this star starts as some real non-unitary boundary condition, and then somewhere when you crank up the coupling, it becomes real. It becomes unitary, and then it annihilates. Because there are examples of this in simpler theories, where some boundary condition for some values of the coupling it's real non-unitary, then it becomes unitary, and then it.
But this presumably maybe you could compute in this non-unitary theory, or maybe not in this non-unitary boundary condition, and you conjecture it's still monotonic.
Well, okay, I think one of the main use of this will be to try to compute it for real means and try to check these things that this picture before, but this we haven't done yet. Okay, so we haven't done the computation for real means. So it's at the moment we just do some simpler calculations. Okay.
The F-theorem can fail if the theory is not unitary, right?
Yeah. I suspect that if the theory is not unitary, this will fail. Yes, or can fail. But again, I want to say that this D star, if it is to merge with D, where it merges, it must be unitary. Okay? But it could be that with coupling it's not unitary. Okay, so we stumbled upon this because of society. I was explaining that this is there is something well known in BCFT case that is a generalization of, meaning that it is well known that if you consider a conformal field theory, you can define a monotonic quantity, a boundary conformal field theory, you can define a monotonic quantity by considering the partition function on half sphere, okay? With the boundary at the boundary of the sphere. Okay, but this, you can also think about it as the partition function of the half sphere is also equivalent to the partition function on anti-de Sitter, because the theory is conformal, okay, and you can do variant balance. Okay, so in a sense, you can say that we are generalizing this thing that John and Canciandani did in 2012, we are generalizing to the case where now we also consider a massive theory in anti-de Sitter, okay? Yes?
This is also what was done in holography, I guess, with these double trace deformations by people like Gubser and Klebanov, I think.
I mean, there is, I'm going to comment on that because I'm going to do the free theory example, and then maybe you can say again, but I think I will address this. So roughly speaking, what is the idea? The idea is to take the logarithm of the partition function ADS with some funny factor in front, which if you ever saw the way these theorems work in CFT, you know that sometimes you have to put these funny factors that change depending on the dimensions. we have to be a little bit more precise because this object is both UV and IR divergent, okay? So let's try to be more precise. So first of all, there are IR divergences because we're computing a partition function, mostly because we're computing a partition function assigned at an infinite volume, right? Usually this is a no-no. But in this case, I mean, we can use rather standard techniques that are common in holography, goes under the name of holographic normalization. What we do is first we put a cutoff surface at some fixed value of our radial coordinate, and then we can reabsorb things that diverge in this limit by using local counter terms at this boundary. Okay, so we don't have to reinvent the wheel for this. There is nothing about holographic normalization that really requires a dynamical metric, of course, so we can use it to regularize the divergences. What about UV divergences? So they are parameterized by possible bulk counter terms, of course. Okay, so this is a schematic form of what a bulk counter term can look like. So there can be some power of some coupling, some curvature to some power, and some UV cutoff to some power in such a way that dimensional analysis works. But you see, when you evaluate these counter terms, typically what do you find? You find some power of the radius, your UV cutoff, and a volume of ADS, okay? So this is where you see that you need to, this volume of ADS can be assigned a finite number precisely by the first item, okay? Using holographic normalization, this I can give it a finite value. And then I have to deal with this lambda UV that is still there, okay? Now, a very important point about the UV divergences is that they are local in the bulk. And so in particular, they are independent of the boundary condition, okay? They are independent of the boundary condition, which means that one very simple way to get a finite quantity is just to take the difference between two boundary conditions for the same bulk theory, okay? So you get this quantity over here. So this is UV finite. And now you can do two things. Either you can test that this is positive if you can flow from B1 to B0, okay? That's your monotonicity. Or you can say that you sacrifice one boundary condition, you sacrifice B0, you say this, I don't know what it is, I put it as a reference, and then I study this quantity as a function of B1, okay? That's another way you can deal with UV divergences. If you don't want to sacrifice any boundary condition, then you need to suffer a little bit more. So one thing that you can do is that you can try to use the partition function on a different geometry, like the sphere, a geometry that doesn't have a boundary. But you know, we have all these curvature counter terms that are going to have a different sign on the sphere compared to ADS. So if you want to cancel them between the two geometries, you need to do some analytic continuation in the radius, okay? Which it's a fancy way to say that you flip the sign of all the curvature terms, okay? And also, if you do this, you also get a finite quantity, a UV finite quantity. By the way, this is also what is done in this paper in BCFT. They also subtract the sphere partition function in order to get a finite quantity. And there is this beautiful thing that if you regulate the volume of ADS d+1, I think here I wanted to put, there might be a mistake here of D versus d+1. Okay, I don't remember now.
Does this also work for two general points on the RG flow? Not two fixed points?
No, at the moment I'm not being so ambitious. I just want to define a quantity for the conformal boundary conditions. So yeah, I don't want to do something in between.
So you only talk about the weak version?
Weak version, yes, yes, yes.
I'm a bit confused about the IR part of the divergences. So
yes.
the UV divergences are local, so it's fine. You just get functions of the metric and it's fine.
Mm-hmm.
The IR divergences are not like that, right? You need to, they're non-local, so you regularize them at the level of integrating the operators before doing the path integral. These are correspond to UV, to relevant operators in the BCFT.
Yeah, they are operators at the boundary. That's what you're saying. Yes.
So how do you know that? So you want to take the universal terms, but like naively I would say, if you have relevant operators, whether you put them or not, it changes the phase. So how do you know that there is a way in which this number you're attaching to a specific boundary condition?
Well, I mean, basically, one way to rephrase this problem is that sometimes there are boundary conditions that have relevant operators, okay? And what this is saying is that when you are there, you need to tune them, okay? That's what we're saying. These boundary operators need to be tuned. Like, the most simple example would be the delta minus boundary condition, right? If you try to compute the partition function for the delta minus boundary condition, you know that there is a relevant O squared operator that you need to tune to be there. So this will require that when you compute the path integral, you take this into account.
Right. So this is part of the choice of theory to which you want to attach. It's not just a regularization. Like there's two different solutions. For instance, in that case, there's two different set of counter terms that make the other divergences go away and correspond to two boundary conditions.
Yeah, but the way I was phrasing it here is more like I choose one boundary condition that I like, and I would like to compute F for that. Then, in that case, I might have the need to adjust the boundary terms. Okay, so this is also what I think Chris was asking. A very simple example. Let's take bulk free scalar. Okay, we all know a free scalar, massive free scalar in de Sitter, I guess. So there are two simple Gaussian boundary conditions, plus and minus, which are the two solutions of this famous equation. One gives the dimension of delta plus to this operator, one gives the dimension delta minus, which are satisfy these inequalities. And then, okay, if we plot these boundary conditions minus and plus as a function of m squared L squared, they disappear, they merge and annihilate at the Bertalanffy-Friedman bound. And you see, this is an example of these things that are sometimes non-unitary, they become unitary, right? The minus boundary condition, if we go past this point, it's a real non-unitary boundary condition. Then here, tac, it becomes unitary, and then it merges with the share, right? And here we have this RG, which is just the famous double trace RG that connects them, okay? So now we need to check that this satisfies. Okay, a sanity check is that this satisfies our proposal. And this check basically has already been done. Okay, it has already been done, but with a different interpretation. The interpretation that was given to it was that people were considering a holographic CFT, so which is a local CFT at the boundary, which in the limit of large n, you can connect two of them by a double trace flow. Okay. And so the computation was done, and then what they were computing the partition function for this local CFT, which is this large n CFT at the boundary, but at the end of the day it's the same, okay? Here I'm just reinterpreting it, and I'm doing the calculation in a slightly different way, putting more, they were computing it, for instance, in this paper, really by taking the sphere partition function for this non-local CFT. Here instead I'm computing it from the point of view of the bulk, but okay, it's a very similar calculation. So one trick you can do, maybe I can skip these details, like you take the derivative of this, then you get the bev of the operator phi squared with this regulated volume in front, and then, okay, you need some integration constant, right? Because once you computed this, you have this derivative. The integration constant, for instance, you can use the difference into B0 at the Bertalanffy-Friedman boundary. Yes?
In this calculation, phi square, how do you regularize UV? Point splitting?
You can regularize, so if you do the difference, it goes away, like I was saying before. So you can do point splitting, for instance, and then the divergence cancels between these two, or you can do any regularization that you like, and the difference cancels between these two.
Yeah, but the point splitting, you can do it like Hadamard, or just removing the singularity like in flat space, right? If you do that.
My point split, this function is just a function of the distance in ADS. I take the distance small.
Geodesic distance, right?
Any distance you like, chordal distance, doesn't matter, it's a distance. And then you take this to be small, and you have a divergence in 1 over this distance to some power, which is completely fixed by flat space, of course, and it is the same here and here. You subtract and this goes away and you get a number. Does it make sense? I mean, it's not...
In my experience, if you just regularize naively with flat space divergence, you get different results.
I mean, maybe you're computing more complicated backgrounds than me. This is like just, you know, ADS, maximally symmetric. Everything is just a function of the geodesic distance, portal distance, whatever you want to call it. And I mean, it's not a mystery how to compute this, I think. Okay, you can do also a similar computation for the massive free fermion. And okay, so this works. Of course, we need to put ourselves in the range of masses for which both boundary conditions exist. As I said, this is just reinterpreting old calculations in this new language. Now let me go to some newer calculations. In particular, I would like to discuss in the remaining 8 minutes the application to... Yes?
Can I ask a question on the previous slide?
Yes.
So just in the end, for like the higher you go in the dimension, the lower this the smaller this RG flow is. I mean, the weaker is this RG flow. It looks like
yeah.
Balanced.
I'm afraid I don't have an interpretation of this behavior as a function of D, but maybe if we think about it, we can come up with some reason.
But you expect that this is monotonic for anything? Like it
Yes.
just becomes less and less.
Yeah, there is a little bit of a technicality that I didn't discuss, which is for D equal 1, actually the unitarity bound stops before, but okay. Yes, it's... I don't have a very good explanation of this behavior as a function of D, sorry. Yes?
Is there more to come? Is your plan to do this for an interacting theory also? Or?
Yeah, I will discuss now some interacting examples.
Oh,
yes. Well, you can judge.
Interacting in the bulk or on the boundary?
Hmm?
You put the interaction on the bulk or on the boundary?
Answer is boundary.
On the boundary?
Yes. Okay, so I want to discuss this example of the long-range icing. Okay, typically these monotonicity theorems, we apply them to RG flows between local CFTs. Of course, this is not the only possibility. There is also a vast literature that I didn't review, sorry for that, on monotonicity for quantities associated to defects, okay? But defects are not the only examples of some non-local or long-range conformal field theories. Another example of interesting long-range model is what is called long-range icing. Okay, so this is the definition like in statistical physics. It's like we take something similar to icing, but instead of just taking the nearest neighbor, we take this interaction that decays with the distance between the sides, it's of power. Okay? And this can be described in the continuum as some non-local Lagrangian, okay? We have this kernel here which depends on the parameter S, and then we deform by, for instance, we have two relevant operators. Let's say we have two relevant operators phi squared and pi to the fourth, and we can study the phase diagram as a function of this. And if we tune this T, the temperature, we have some interesting second order phase transition, at least in some range of the parameters that now I'm going to discuss, which is known as long-range icing CFT. Okay? Yes?
I thought that the long-range icing can be thought as a defect in a higher dimensional theory.
Well, that's precisely what I'm going to do. If you want to think about it as a defect, you might have to, for generic S, it depends where you want to stop yourself. Like you can do it for generic S, but then the dimension needs to be a continuum parameter of the bulk. Alternatively, you can do it with ADS and you can take the dimension to be.
The dimension of some bulk field.
Yeah, you use the mass. Like, you use the mass in the bulk instead. Yeah. Okay. just remember here there is this S parameter that controls non-locality, and here if I use this Lagrangian, I will have dimension of the scalar field, which is d minus S over 2, okay? And then I deform it with this quartic interaction. Yes, exactly what I was saying to Andrea, that this can be realized as an interacting boundary condition of the massive scalar field in ADS, okay? I mean, this is not something that we invented, it's well known. But now we can use what we just discussed to also assign to this long-rangizing CFT F quantity, okay? Which, according to what we just conjectured, must be monotonic along RG flows that connect to the long-rangizing CFT, okay? Now, let me review some well-known RG flows that connect to the long-rangizing on which we can test this conjecture. Okay, so sorry, this will be a bit fast. So let's consider the plus and minus boundary conditions that we discussed before, okay? And now, in this paper, they show that there is this kind of diagram of RG flows related to the long-rangizing. So on the green line, there is the boundary condition plus times a decoupled local Ising CFT in 3 dimensions, in boundary dimension, whatever is the dimension of the boundary. And while this is just the minus boundary condition, okay? So the dimensions delta plus and delta minus are d plus minus S over 2, okay? And then in this intermediate regime, where this delta sigma is the dimension of the sigma field in the local 3D, local d-dimensionalizing, in this range, you can define the long-rangizing CFT either flowing from the minus boundary condition with the quartic coupling, okay? Or you can define it flowing from the plus boundary condition with an Ising sector with this kind of interaction, okay? So now we have some things to test. Well, actually, the tests that we can do are, for instance, this. No, we can test this RG flow, this RG flow. Here, more than testing, we can give some bounds for what can be the F quantity of the long-rangizing CFT. Okay, that's what we're going to do. Okay, so these are some plots in 3 boundary dimension. Here we are plotting the minimum between the F of the plus boundary condition and F minus plus Ising, okay? So, which are the 2 constraints that come from the 2 RG flows. Oops, sorry. And you can do a similar plot in 2 dimensions. So these possible values for the F of the long-rangizing allowed by this monotonicity. But then, okay, the real test actually that we can do is, for instance, we can test. Okay, here I chose a bit weird variables on the 2 axes, but what I'm testing here is these 2 RGs, okay? So the one from plus times Ising to minus, or the one from minus to plus times Ising, okay? So what is the prediction from the existence of these 2 RGs? The prediction is that when S is smaller than S minus, this F must be bigger than this F. And when S is bigger than S plus, this F must be bigger than this F, okay? And indeed, you can see that, you see, here we are in S smaller than S minus, and here we are in S smaller than S plus, and this is the difference between the 2 lines, okay? So here it's negative, and here it becomes positive, okay? Both in d equals 2 and d equals 3. So this is just a weird rescaling in such a way that both in 2D and in 3D, I made the S plus and S minus to coincide.
Okay, that's why they cross at the same point.
This is a mystery. Like, we don't know why, when we did the rescaling, they meet, like with the known precision for delta sigma and F of the Ising, they meet in one point. We don't have any idea why. Okay. because we just did this scaling to do one less plot in the paper, but then we found this weird match. I don't know, we don't have reason for this. And okay, very briefly, we also did the check in the ON sigma model. Also, this interacting, but the computation is very easy at large n, and it works. So you can see that they coincide, the F of the Dirichlet boundary condition and the F of the symmetry breaking boundary condition at the transition point. And okay, so let me say some possible future directions. Obviously, it would be nice to have some more solid argument of why this monotonicity is true. And maybe, so as Matthew was mentioning, it would be very nice to try to apply to Yang-Mills, no? For instance, what you can try to test is this idea that after the merger annihilation we go to Neumann. A necessary condition is that then F of D must be larger than F of Neumann.
Just about the previous model.
Yes?
How do you think about these limits of this flow, of the Rastelli flow, where you have, you know, Ising and then the decoupled free field, generalized free field? Because I guess Ising has its own stress tensor, like the green line, maybe red line.
This one,
Yeah,
yes.
The extreme endpoints. Like, how do you think about that in your picture? Because Ising has a stress tensor, right?
Yeah. So the way, so there is a subclass of boundary conditions for a quantum fit theory in ADS, which you also add some local sector completely decoupled. Okay, of course it's a bit boring, but you can do that, why not? And then when I'm computing F for this case, I will just get the contribution from the bulk, and then I will get plus F, the sphere partition function for this object, okay? Okay, and I guess I'm done. Thank you.